goal today is, during this week, is to define holomorphic functions in domains which are not simply connected. And a typical example for us would be complement to 0, which is like a basic non-simply connected domain we are studying. And a typical function we want to make sense of is, say, logarithm. And then it immediately turns out that it's not a function in the sense we know it anymore. So classically, such objects were called multi-valued function. But what I'll do, I'll divide the material in two parts. So today there'll be like geometry or topology of this story, and I'll try to tell you this story from the beginning, from scratch, and in the generality we'll use it. And then on Thursday we'll do the analytic part. Okay? So you'll be surprised maybe because I'm not immediately following the book, although the book has the same, I'll mention where my story meets the story in the book. So typical words from the book are argument of a complex number and so on. But you'll see. So so maybe the slogan or so we understand well. Holomorphic functions. In simply connected or say star-shaped domains G in complex numbers, and we want to do the same for G non-simply connected, for example, G being C without 0, or G being, say, unit disk. And so on. So we want to approximate them by simply connecting. So it's one way. So one way we know. So first way, covered by disks. So covered by something simply connected. So say by disks. Covered by little disks. And then do something local to global. But there's second way which we'll be discussing today and on Thursday. And this way is mathematically called use covering spaces. So the story today will be about covering spaces. With the basic examples, which basically illustrate what we're interested in. So I think, so that I would not repeat the same words again and again, I'll start from the very beginning as it goes in topology. So notions from topology. And in a way, this looks strange on one hand, and on the other hand, it's like discovering that your whole life you were speaking in prose. So that's what we've been doing. We've been using topological notions all the time. So let's start from definition. So a topological space X is a set with a chosen class of open subset of subsets called open, such that first of all empty set is open, the whole X is open, any union of open sets subsets is open, and a finite intersection of open sets is open. So it's part of the data. Now, why it's related to our everyday geometric or analytic life? It's because if X is a metric, so example, is a metric space, for example, X is a subset in Rn with the usual distance. Then X is a topological space with U in X open when for any X in U, well, you know that, there exists an open ball K X R for some R greater than 0, which is also inside U. So yeah, we've been talking about topological spaces all the time. So in particular, complex numbers is topological space. Any G a domain in complex numbers is also topological space. So there are maybe 3 more or maybe 4 more topological spaces which appear all the time in our real life. So a real line is a topological space because it's one of the examples I mentioned. It's a metric space. An interval is a topological space. Now, yeah, a half line is a topological space. And finally, unit circle S1. So this is, let's say, complex numbers. Absolute value of Z equals 1 is a topological space. So I think that what you have on the board is more or less the whole class of, all topological spaces we've been using in this course, but I just wanted to have them on the board. So second definition I'll recall and use is that a map F, say from Y to X, between topological spaces is continuous if for any U in X open its preimage in Y is also open. So the whole epsilon delta language as you know it is about this. So good. Yeah, and maybe the last word about maps is that x and y, so every such situation needs its own notion of isomorphism, so it's x and y are homeomorphic, like isomorphic in topological sense. If there exists f, y to x, and g from x to y, both continuous, such that fg is identity y, identity x, and gf is identity y. Okay, so I just made fast train definitions. Now, different notions of connectedness. So we met one notion already, maybe for domains, but of course I can say it in general. So X is called path connected topological space if for every 2 points x0 and x1 in X there exists a continuous map from unit interval as a topological space to X with gamma of 0 equal x0, gamma of 1 equal x1. We had it for subsets in C, but there's another notion of connectedness, another more topological notion. So X is just connected if the following is true. Whenever X is a union of U1 and U2, disjoint union. Both open. U1, U2 open. Then either U1 is empty or U2 is empty. So, I mean, I can draw it in an easy picture. So, what's forbidden? So, suppose we have a space which looks like this, a union of this and this. So, obviously, this thing is not connected, but so both of them, let's say, so our X is union of these two, so X is K, say, 0, 1, disjoint union, K of, what's your favorite number, 15, 1, as a subset in C. So definitely it's an open subset, and it's a union of two, disjoint union of two open subsets. So it's not connected. So not connected. Now there's an easy lemma. One important observation or fact or exercise. An interval is connected. So you can do it from scratch, from the definition. Now there's a lemma. The lemma says that if X is connected and we have a continuous map F from X to Y, continuous, and let's say surjective. Otherwise, I would be talking about the image. Such that so then the image then y is also connected. Okay. Proof. Just one line. Suppose not. Then y is disjoint union of u1 and u2. Well, but then take preimages of u1 and preimage of u2 in X. So these are open. So what do we know about these ones? They are both open because f is continuous. And X is their disjoint union. Then one of them is empty. But then same true about one of u1, u2. And this is a contradiction. Okay, in view of what I wrote on this blackboard, let's compare the two notions of connectedness. So, proposition. If X is path connected, then X is connected. So notion of path connectedness is stronger than the notion of connectedness. Proof. Well, suppose not. And we have X realized as union of two non-empty open sets. Non-empty open. So take our favorite point x0 here and take our favorite point x1 here. By definition, there exists gamma continuous from unit interval to x continuous with gamma of 0 being x0, gamma of 1 being x1. So take gamma star. This is our notion, our notation for the image of gamma. It's a subset in X. So then, gamma star is gamma star intersected with U1. Disjoint union, gamma star intersected with U2. Both open. In gamma star. Now, none of them can be empty because x0 is in one of them and x1 is in the other. So both non-empty. So what do we get? We get, so the same map gamma can be seen as a surjective map from 0, 1 to gamma star, now surjective since it's on the image, continuous, with 0, 1 connected, and as explained, gamma star not connected, because it's a disjoint union of two open sets. Great, then this is a contradiction. So I proved that connected, that path connected implies connected. Now we'll talk about the main topic of today's lecture, or maybe main definition. It's still notions from topology. So main definition, main topological definition for today. So we have two topological spaces, y and x are topological spaces. A map, a continuous map, phi, from y to x is covering. I announced that we'll be using coverings of x, or covering space maybe. If so one small thing, it's surjective. And now there are two important things. So pre-image, so for any point x in x, pre-image of x in y is discrete. So maybe I'll write it in short, does not have accumulation points. But intuitively it's clear what it means to be discrete. Just a discrete set. And finally, for every point, so this is the most important one, every point x in x, there exists open neighborhood u of x such that if we restrict pi to its preimage, so I mean, if you take its preimage, then it's homeomorphic, so basically isomorphic, to the product of this discrete set times the neighborhood itself. I'll draw what people usually draw in this situation. So typical picture. You have your x here, and y is just a few copies of x above it. So every point has a neighborhood such that its preimage is discrete. So this is together, these are preimage of x, and preimage of this neighborhood is this joint union of these neighborhoods. Each of them is homeomorphic, isomorphic to the original one, but we take the union of them. Okay? So these together, maybe I should start using colored chalk. These together are pre-image of U of X. So, yeah, the example, because this was done for examples. So, of course, main example is identity map. Identity map is definitely satisfying all of these. Pre-image of every point is this point itself. Pre-image of every neighborhood is this neighborhood itself. So, true. Another example is if you take the joint union of a few copies of X, say 3, and it maps to X. Also, pre-image of a point is just union of this point here, and this point here, and pre-image of a neighborhood is disjoint union of the same 3 neighborhoods. So this was not interesting, and this was very generic, but here is the one which we'll use. Consider pi, which goes from unit circle to itself. So a point here was a complex number of the form cosine theta plus I sine theta. So then let it go to the same taken twice. So, or in other words, if you think about this as a complex number with absolute value of z equal to 1, z goes to z squared. So it's clear that for every complex number, there are exactly 2 square roots. I mean, for every complex number with absolute value equal to 1, there are exactly 2 square roots, both of them on the unit circle, and locally the map is 1 to 1. Right? So if you have one unit circle which is the target and another unit circle which is the source, if you take a point, then there are, so this angle is, say, theta. But then theta over 2 is good, but also minus theta over 2 is also good. No, not minus, but pi plus, yeah. This one is also good. This is pi plus theta over 2. So both of them, when you take this map, go to the same point here. So pre-image is just the union of these 2 points. And if you take a neighborhood here, then its pre-image will be union of a small neighborhood here and a small neighborhood here. Okay? So this is a model situation for covering, and that's basically why we'll be interested in this. Now, one more example. So we'll see that this example will be universal in a sense. Let's take y equal real line and take x equal unit circle. And let's define pi from R to S1. I think you should understand what I'll be doing. So theta, which is an element in R, goes exactly to cosine of theta plus I sine of theta, which is a point on unit circle. So I claim that this is a covering. So if we have some point, then, well, there are infinitely many points in the preimage, and all of them, so for any z, absolute value of z equal to 1. So what's the preimage? That's theta cosine of theta plus I sine of theta equals z. But then we can choose one of them. And start adding 2 pi n, where n is in z. So in terms of the real line, the preimage looks as some particular theta node, and then many steps in all directions. So this is the preimage, right? And it's clear that if we're interested in neighborhood of this point, then there'll be, so if this neighborhood is small enough, then there'll be many small neighborhoods around each of these points. So the preimage of a neighborhood will be this joint union of small neighborhoods around all of these points. By the way, in this notation from the book, for this particular covering, pi from R to S1, which is a subset in complex numbers, preimage of a given point has a name. It's a subset. It's called small argument of the point z. And it's a subset in real line. It's a discrete subset. Okay, so having spoken about this, let's move on with the small observations and with the dictionary. So, a very small observation. Suppose we have a map, pi, from y to x, which is a homeomorphism. So, i.e., there exists another map, pi inverse, from x to y, both continuous, with pi inverse being identity and pi inverse pi being identity. Then obviously it's a covering. Then pi is a covering. That's clear because pre-image it consists of just one point, and if we have a neighborhood in X, apply pi inverse and you get a neighborhood of that point in Y. And it's an isomorphism. Isomorphisms definitely keep neighborhoods and so on. So typical example is like this. So let's consider a map from R to R plus. Do you know a distinguished map from R to R plus? It's exponential map. So say, I don't know, T goes to X. So definitely it's a homeomorphism. The map backwards is called logarithm. Any positive real number has a uniquely defined logarithm. So it's a cover. Now, another remark. Suppose we have a covering pi. And say another map, I need a notation for it. Let's choose, say, rho. From Z to T is also covering. Then we can take the product. So this is a covering. So remark is that if you have two coverings, then the product is a covering. So in particular, if rho is homeomorphism as above, then pi cross rho is a covering. So now we're coming to the main example. Consider a map main example. Consider a map. So we had two of them already. So pi is a map from real line to S1. And this takes theta to cosine of theta plus I sine of theta. And consider the map rho from real line to R plus, which takes, let's say, so for some reason I'll denote this argument here R. R goes to X of R. So both of them are coverings already by what we discussed. So both are coverings. So then in view of the observation, let's take the product. It goes from R cross R to S1 cross R plus. By the way, this R cross R has another notation, R2, or also C. And this S1 cross R plus is a typical way to realize a non-zero complex number in polar coordinates. This is the radius, and this is the angle. So then, this is C without zero. Now, let's see what this map does. It takes the radius to the exponential of the radius, and it takes the argument to this. So if you think about it, so this, in terms of complex numbers, this will be the real part, this will be the imaginary part. Okay, so then by formula, I cross rho of whatever, R plus I sine I theta is exponential of R. Well, I can write times cosine theta plus I sine theta. So what's the outcome? This map from C to C without zero, well, both of them were surjective, and so this is a surjective map. And by what I said, it is a covering. So let me summarize, and then we'll go for the break. Prove the following proposition. The map X from complex numbers to complex numbers without zero, taking well, R plus I theta to X of R times cosine theta plus I sine theta is a covering. Saying that it's surjective, pre-image of every point is discrete subset in complex numbers, and every point has a neighborhood whose pre-image is a disjoint union of its copies. Okay? So let me stop here. I need a certain trust from you till the